Hello everyone and welcome to another Stat 437 lecture video. In today's video, we are going to be doing an introduction to time to event data. Now, time to event data is the type of data that we analyze when we're talking about survival analysis, which is sort of the next big topic that we're addressing in this course. So we spent the first chunk talking about longitudinal data. We're going to spend the last chunk talking about survival analysis. And the goal of survival analysis is to analyze time to event data. So in today's lecture, we're going to talk about what time to event data is, what makes it special, the challenges that are going to arise when we try to analyze it, and sort of give you a feel for what it is that we're going to be trying to do for the rest of the term. So with that, we can open up the slides here and talk about what time to event data actually are. So I'll begin with two separate examples to give you a good overall feel. The general sense of time to event data is, as the name would suggest, it's data on how long it takes until some event that we care about happens. So to make this concrete, one of the symptoms of COVID-19 is the loss of your smell, your sense of smell or taste. Okay? And so you could ask, how long from the onset of this symptom will it normally take for someone's sense of smell or their sense of taste to return? And there was a study that was done on it, and it says that 72% of people with COVID-19 who lost their senses of smell or taste reported that they recovered them within 1 month, I think. Yes, after a single month. And so that sort of, contextualizes this question a little bit. But this question of how long until your senses start operating correctly again is a question that we can address with survival data, right? And so the setup there in general is we start measuring when someone loses their sense of smell, and then we every day are sort of following them asking, did it return? And after a month, we're saying that 72% of people do. And what we're going to be talking about throughout the rest of the term is ways of sort of characterizing that and estimating those distributions without just reporting this 72% after a month number, right? There are better ways of sort of describing this entirely. And so that's one example. Another common example that you're going to see is length of careers. So I have this infographic here from the Wall Street Journal, and what it does is it looks at, for different positions in football, how long is an average player's career, right? And so it goes through the different positions from the offensive lineman down to the wide receiver. You can see that it's somewhere between 2 and a little bit over 2 years to almost 4 years are sort of the range of average lengths, and there's lots of variation in that. But generally speaking, we can sort of look and see how long do players actually spend. So this takes the same format as that question that we were asking about the sense of smell, right? We can say once someone starts playing in the NFL, how long until they've retired or they're pushed out of the league for other reasons, right? And so there's sort of a lot of obvious questions that take this form. Survival analysis makes it sound like we're talking about time till death. How long do you survive for? And that's where the name comes. But you can think about it in sort of this case of symptom onset, or you can think about it in terms of careers. You can think about it from sort of a manufacturing process. How long can you use a product before it wears out, right? Any question that is sort of measuring the time, and then we just want to know, did an event happen or not? Any of these questions can sort of be answered using the tools of survival analysis. And so hopefully those two examples show you sort of how broad this topic of analysis is. But again, there's sort of these more natural ways of applying them to the biostatistics context. So in time to event data, generally speaking, is longitudinal data where we're measuring the time until an event occurs, and we want to know, what are the associated risk factors, what are the predicted lengths for any individual, what modeling techniques can we use to sort of characterize how long until some event occurs. When we're doing the analysis of it, we will call it survival analysis. There's other names for it, but survival analysis is the most common in the biostatistics literature, so that's what we'll sort of focus on. But it goes by a few names, but any questions that are sort of how long until something happens, it's the same setup that we're going to be working with. So the brief overview, the overall goal is characterizing the time until an event, e.g. the death of someone, and trying to characterize that complete distribution in any number of ways. The reason it's taking place in this course is because this is still longitudinal data. It's just a particular kind of longitudinal data, right? So we're following an individual, and instead of measuring some outcome at every point, the outcome that we're asking them about is, has the event happened, right? So you look at them day 1, has it happened? No. Day 2, yes, no, right? And you keep following them until the event happens. We'll oftentimes have to deal with what we will call censoring or truncation, right? So when we were talking about the standard analysis of longitudinal data, the big concern that we had was that these data were correlated. The correlation isn't going to be so much an issue with time to event data, and we'll see that because there's sort of different ways of formulating the process, but time to event data is going to be plagued by censoring and truncation, and we'll talk about exactly what those things are, but they sort of make the analysis question more difficult. So censoring refers to individuals who we stop observing before their event has happened, or at least that's typically what we mean by it. There's a few different kinds of censoring. So, if you think about running a study where you want to say, what are the health impacts on lung cancer, for instance. If you follow a big group of individuals and you wait until they've developed lung cancer, well, a large portion of the people you're following, your study is going to end before they've developed lung cancer. And so what that means is you've observed them for a window of time, and that gives you some information about, when they would develop lung cancer, but it doesn't sort of give you all of the information. Now, there's going to be other people who, you're interested in this lung cancer, but they die of a heart attack while your study is running, right? And so you can think about those people in sort of the same way, where had they not died of that heart attack and had, everything continued going for sort of as long as they could, eventually they might have developed lung cancer. And so, we have to deal with these issues of this incomplete data. With truncation, we sort of have a related but slightly different issue, and that's where individuals are excluded from a study because their event is not happening within a defined window. So a common way to think about this is if you want to say, study heart health for individuals, you might exclude anyone who has not or who has had a heart attack in the past, right? And what this means is that intentionally, you're looking at only a sample of people who did not have heart attacks by the time they were 50 years old, say, right? And so by excluding other individuals, you're sort of limiting your analysis. You have to work on this conditional distribution where, given these individuals had not had a heart attack yet, what is the likelihood that they survive beyond a certain point? And so we'll look at both of these problems in sort of more detail, but instead of thinking about correlation as the key thing that we're fighting against, you should be thinking about censoring and truncation as the key points that we have to take account of. So what are the key components of time to event data? There are 3 that we will discuss, and the first is a specific time origin specified for all individuals, right? So on this little diagram here, if we think about this as being a timeline for an individual, we have our time origin, which we set to be 0. Now, this might seem obvious, but it's important that we specifically define what we mean by this, right? And we looked at this a little bit with longitudinal data where we talked about using different timescales, right? But the time origin of 0, we can define to be sort of anything that we want to be. We just need to make sure that it's clear. So some examples, maybe you start looking when your study starts, right? And if you start looking when your study starts, that's easy. Everyone sort of has the same origin and it's the same in calendar time. And then you might just have to account for people who are of different ages when the study began. You might also want to use, someone's age being 0 as the time origin, right? And then what you have is at the start of your study, now it's people's time origins aren't at the same point in calendar time, but they're still clearly defined to be when they were 0 years old, right? And so defining this time origin is going to be important, and it's important that it's defined and interpretable for all individuals. We also need to clearly define what the event occurrence is, right? So in our example where we were talking about lung cancer, and we had mentioned that an individual, might die of heart disease. Well, if you think about this as being a slightly different study, maybe you wanted to know how long do people survive once they have lung cancer, right? And so if you're looking at people who have been diagnosed with lung cancer, a lot of them are going to die of this cancer, but some of them are going to die of something that's not lung cancer, right? And so if you're in this study and you have someone who dies of a heart attack during your lung cancer study, or they die in a car accident during your lung cancer study, well, you have to make sure that you're noting that this was not the event of interest occurring, right? So it's not time until death, it's time until death of lung cancer during this study window. And so, again, it's one of these situations in statistics where we have to be really careful about clearly defining what it is we're talking about so that we know how long has the time, how long has it been since whatever point we're starting to count from, and when did the event specifically occur. Okay? And so, with clear definitions of both of those, you can sort of measure this timeline as you need to. And that brings us to the third component, which is the measurement scale. Are you measuring in years? Are you measuring in calendar days? Are you measuring in the age of the individual? You can also think about it if you're looking at products. Maybe it's a light that you want to know. How long does the light last? And perhaps it makes more sense, instead of measuring this in hours, to measure it in cycles of the light being turned on and off, or something similar, right? So if you've defined what the origin is, when the event has occurred, you know specifically how to assess that, and you know how you're measuring time, then we have sort of all of the components we need for time to event data to be well defined. So I'll clear those boxes here. And just note that we're differentiating between discrete and continuous time. So if the scale you're using is discrete, then we will use a particular set of methods. And if the scale you're using is continuous, we'll use different methods. This is sort of, what you've been seeing throughout your statistics courses already, and that will become more apparent during the analysis of survival data. And so we'll start with methods for discrete time to event data, and then we'll look at continuous time to event data. And, all of the same considerations are going to apply, right? Oftentimes you might measure something that is technically continuous, but you want to treat it as discrete, or vice versa. And we're going to have some flexibility there, but just note you have to make this decision. And that's going to be informed by the time scale that you're working on. So what makes survival analysis special? We've already touched on this a little bit, but there are two particular traits that we're mostly concerned with. The first is censoring. So the idea with censoring is that it is any time where you know the window that an event would have occurred in, but you don't observe the specific time. Okay, so there are two different types of censoring that we're oftentimes going to talk about, and that's either left or right censoring. And so we'll take a look at this first timeline here. Okay, and so what's happening is we have our time origin at the 0 here, right? And so we've defined some clear time origin. And then we know that the event occurrence would happen at some time t, right? And so this person's under observation, but the observation window ends here at a time that we're calling c. And so what ends up happening in this situation is that the actual event would have occurred at some point into the future at this time t. And so we don't observe that event time, and so we say that they were censored. And in particular, this is going to be right censoring because the event occurs to the right of the censoring window. Okay? And so the ways, the most common way to sort of think about this would be if your study ends, for instance, or if the patient dies, or if they move away and they unenroll from the study that you're looking at, or you just lose follow-up with them, whatever. This is the most common type of censoring to think about, and it's going to be sort of the main focus of what we're looking at. So we only observe this individual for a set period of time, and we know that the event occurs after that time. But what's important to think about with this is that we still get some information on the survival time, right? Because we know that this person at least lasted this long, right? So it's not like they're totally missing from our sample. They've provided us some information. And in particular, maybe they provide us a lot of information if most people are sort of having their events over here, right? Then something about this person suggests that their survival time is much better than average, right? And so we need to take into account the information by this individual. The other form of censoring, which we call left censoring, is sort of the opposite. We have our time origin and the end of observation here, but the actual event occurrence happened before we started observing the individual, right? And so in this case, we don't observe the event happening because at time 0, the event had already happened. And in this situation, we're dealing with the case of knowing that this individual did not sort of even survive until whatever we've defined the time origin to be. And so obviously in this setting, the time origin could not be their birth, right? Because we know that the event occurred before we started observing them. But the point is that when they're under observation, the event's already occurred. And so a way that you could think about this is if, for instance, the event is the time that you started smoking cigarettes, right? When you have an individual who you enroll in your study, if they've already smoked, you might ask them, when was your first cigarette? And, that could have been years ago, right? And so that is censored in this opposite direction. And in particular, if you're thinking about that cigarette example, people aren't going to be able to report very deliberately or very specifically very often, right? If someone started smoking when they were in their teens and you're talking to them when they're 50, they're probably not going to remember down to the day when they started smoking. And so we're into this situation where we have an observation window for the individual, but the event occurred before then. And so we would call this left censoring because the event occurred to the left of the observation window. Okay? So an individual who never has an observed event in your window is said to be censored. We can talk about left or right censoring based on whether the event happened before or after the period, right? So left censoring happened before the observation window, right censoring happened after the observation window. An individual who we lose to follow-up, so who drops out of our study, who dies, who the study just ends, that individual is going to be said to be right censored. And there are 3 different ways that we can think about right censoring occurring. Okay? So the first way is type 1. And this is what we might also call administrative censoring, and that's where the censoring time is set and predetermined in advance. So when you set up your study, maybe you say, we're going to follow people for 5 years. And after 5 years, our study is over. Okay? It means that anyone who doesn't have an event within 5 years is going to be censored in your study. And that's okay, but that's sort of pre-known. Nothing is random there. The only thing that would be random is the number of individuals who end up being censored, right? But the time is not random, and it's sort of fixed, predetermined. Type 2 censoring is where instead of specifying a time at which we will censor individuals, we specify a number of events that we want to occur, right? So if you start with a population of 1,000 people in your sample, you might say we were going to follow them until 500 of them have had the event that we care about. And this is sort of an effective way at getting a sample size that you need to make good estimation. But here, the censoring time is going to be random, but the number of people that you're going to have been censored is going to be fixed based on your total sample size. Then, with random censoring, both the censoring times and the random quantities themselves are both random quantities themselves, right? And so in this situation, you're thinking about sort of indefinitely following people, and then eventually they're censored or whatever, okay? And so while type 1 censoring will oftentimes be planned in, or type 2 censoring, we're going to treat a lot of censoring as random because we can accommodate it sort of through the procedures that we're going to be looking at. If you ignore censoring, you will bias your results, and you're also ignoring much of the information that you've collected, right? So as I was saying, if you watch someone for a whole period, that whole period of 5 years, and then you just throw away their information, well, there's an individual that you know survived past that 5 years. And so to start, you're biasing your results downward because you're only looking at people who actually had their event in that window of time. And second, you're making it less efficient for estimation because you maybe started with a sample size of, 1,000 people, and only 400 of them had the event, and so you're throwing away 60% of your data, right? And so ignoring censoring is not advisable. But we're going to look at sort of ways that we can accommodate this without making our lives too challenging. The other piece that makes survival analysis difficult to do is truncation, okay? And so here we have this plot, and the idea is that along the x-axis here, we have the calendar time in years, and along the y-axis, we have someone's time since birth, so their age. And so all of these lines are coming out at a 45-degree angle, right? And so they're increasing in 1 year for every calendar year that passes. Now, the basic idea with truncation is that we say we fix some time point d here, okay? And the idea is that these lines stop tracking once the event occurs, so maybe the event's death in this case. And so what we're looking at is only these people who are still alive after this time that we thresholded are going to be allowed into our sample, right? So we're only saying people who did not have the event at time D are available here. And the problem with this is that it's going to start to limit or condition the sample that we're working with, right? Because now instead of being able to talk about the full survival distribution, we have to talk about a conditional survival distribution. We can only talk about, for people who were alive after time point D, this is what the survival distribution was. And in particular, this is an important thing to note because something may have happened, sort of in this intervening time that dramatically shifts what the survival distribution is. And so then people who survived past it have a knowably different distribution than for D. Okay, so that's the basic idea with truncation. But in words, truncation occurs when individuals have been excluded from your sample based on when their event occurs. So again, we can have left or right truncation. So left truncation considers only individuals who had not had an event by the time of the origin. Okay, so you're truncating anyone who had that event at the left-hand side. You don't include them in your study. Whereas right truncation considers only individuals who have an event by the end of the study. Okay, and so the difference between truncation and censoring is that with truncation, these people aren't even recorded. Okay, so your sample, you are sort of doing a sampling bias where you can only look at people who say had the event occurred. Now, why might you have this type of thing happening? Well, if you turn to, say, hospitalization records, right? Hospitalization records are only going to record people who were sick in the hospital. And so if you're using that as your data source, then by definition, only people who were hospitalized are going to be in your study, which is going to be this form of right truncation. Okay? And so it's a sampling bias, and whenever we're dealing with sampling biases, we have to restrict the population that we're dealing with. We have to acknowledge that our sample is not a true random sample, and we need to do conditional analysis to get around that. So when you have truncation, you must perform conditional inference in order to make valid conclusions. There's no way around that. It's the only thing that we can do because our sample's not representative of the full sample, it's representative of the conditional sample, conditional on either the time being above a certain value or the time being below a certain value. Okay, so that's the very quick, brief rundown on what time to event data are. So to sort of recap, time to event data measure the event times for some outcome of interest, right? So some specifically defined outcome that we care about. Survival analysis is the analysis of time to event data. So it characterizes how long until the event of interest occurs. And, we might be looking at risk factors for this. We might be trying to characterize the distribution. We might be answering specific questions, but anything that's sort of analyzing time to event data, we call that survival analysis. The primary hurdles for dealing with survival analysis are censoring and truncation, where censoring refers to individuals who are included in your study, but who don't have an observation during the study window, whereas truncation refers to individuals who are excluded from the study because of the lack of an event relative to either the start or the end of the study. So for the next few weeks, what we'll be doing is looking at different methods for handling time to event data. And so you'll get, much more familiar with all of these concepts, but that's the basic rundown. Of course, if you have any questions at all with anything that we've talked about, please reach out to me and ask away. And otherwise, in the next video, we'll start to sort of define our notation and begin to look at this in a little bit more detail. So I'll see you all then.